Hello, this video will give an introduction to entropy and the second law of thermodynamics. So first we need to build an idea of why we need the second law of thermodynamics in the first place. To review, we have the first law of thermodynamics, which is that the change in internal energy of a system is equal to heat plus work. So this means that um, the change in energy of a system is dependent or is the sum of the heat, so the energy that's transferred due to a difference in temperature between a system and its surroundings. This is heat. Plus the energy that is transferred due to work being applied over a distance parallel to the direction of that force. So work here, remember, work is the dot product of force and distance, or force in the parallel direction of distance. So this is work. And then these both can change the energy inside of a system by transferring energy between a system and surroundings. So these work between a system and its surroundings, But this represents the conservation of energy, because if heat is zero and work is zero, meaning in a closed system, there's no energy being transferred in or out of the system and its surroundings, then the change in energy is also zero. So this is the first law of thermodynamics. So first law. Now, this thing about the conservation of energy here is that it is not inherently like reliant on the direction of time, and that it's based on the symmetry of time. And what does this mean? Well, it means that, so to conserve energy, um, time can flow either backwards and forwards, and either way will lead to the conservation of energy. So conservation of energy itself doesn't like determine the flow of events or the reversibility of processes or time. So let's take an example where we put an ice cube into a glass of water that's warmer than the ice cube. So let's have an ice cube here. And this ice cube is cold, and it's colder than this water that it's put in. Now we know from intuition, from observations before, that as time passes, the ice cube will melt and the water will get cooler. So the ice cube here will lose energy as time goes forward here. And so the ice cube, or no, the ice cube will gain energy because it melts. So it gains energy from heat, through heat from the water. So ice cube will gain energy, and then the water will lose energy. So because its energy goes into the ice cube to reach a state of thermal equilibrium. And so in the end here, after a long enough amount of time passes, we'll just get cooler water. So this water will be at a lower temperature than this water, but then the ice cube will have fully melted. And this represents thermal equilibrium. So this is equilibrium. So this, we know, conserves energy because the ice gains energy and the water loses energy, and at the end they are in equilibrium. However, what if we consider time going backwards, such as what if we have a glass of chilled water that an ice cube suddenly forms in that? So the ice cube actually releases energy into the water and grows bigger over time. Now that would be opposite to what we think would happen if we put an ice cube into a glass of water. The ice cube doesn't grow bigger and the water doesn't get hotter. The water gets cooler and the ice cube melts. However, if let's just say that the water spontaneously starts freezing at one point and turns into an ice cube and cold with warmer water surrounding it, that means that the ice will lose energy and the water will gain energy spontaneously. Now, this doesn't violate the conservation of energy, because as you can see here, it's still a net change of energy. The net change of energy is still zero. However, we're going backwards in the process. And this, we know that this can't actually happen in the real world. Um, because well, given that this is a closed system, so there has to be another thing acting that's preventing time or this process from reversing from what we normally perceive it to be, and that is where the second law of thermodynamics comes in. So this deals with entropy, which is a state property of a system. And it's a state property and a state function, just like volume or mass or temperature is a state function in that um, a system will have a certain amount of entropy and it can decrease or increase. But the second law of thermodynamics says that the net entropy or the net increase or decrease of entropy inside a closed system has to be positive. So entropy or has to be non-negative. So entropy can never decrease in a closed system. So what really is entropy? Well, entropy, we write entropy with the variable S. So just like work is Q or I mean heat is Q or work is W, entropy here represented by S is can be described by the unavailability of a system's thermal energy for conversion into mechanical work. So how much energy is not available for conversion to work. So let's consider like this ice cube inside of water here. So there's a temperature difference between the ice cube and the surrounding water, which means that um, the temperature difference leads to an energy transfer through heat. And that can be converted to work, or that can be used for work in a different scenario. Now, if we look at the water here just by itself, the chilled water, there is no temperature difference, meaning you can't extract work from this system. So this will have higher entropy than this. And so entropy is the unavailability of energy to do work. And so as processes reach equilibrium, they lose the ability to do work and entropy increases. Now this helps to explain why certain things happen in a certain direction. Like if you drop a rock off of a cliff, it falls down and it stays at the bottom. Rocks at the bottom of a cliff don't spontaneously take in energy from its environment and then jump up to the top of the cliff, because that would violate entropy. Because by being at the top of the cliff, it increases its ability to do work because it increases its potential energy. And so energy is a state property of a system and it never decreases in a closed system. So the second law of thermodynamics states that just that um, entropy never decreases. So in a closed system. So the system must be closed because entropy can decrease or increase in parts of a system that's open, but the net entropy change is always going to be non-negative inside a closed system. And so what this means in equation form is change in entropy here, change in S, is going to be greater than or equal to 0. Now, that change in S is equal to 0 whenever a process is reversible. Because if something is reversible, then the entropy change in entropy in both directions has to be non-negative. And the only way that can happen is if it's 0, because if entropy had a positive change in one direction, it follows the second law. But if you reverse it, that becomes negative, and that would violate the second law. So if a process is reversible, entropy change has to be 0. Now, if the process is irreversible, then change in entropy is greater than 0. So this is for irreversible processes. And then everything in nature that happens naturally is irreversible here. So like if you melt an ice cube, or if you throw a rock off a cliff, or let's just say you drop a drop of food coloring into a glass of water, the food coloring will disperse. It won't clump together after it's dispersed. And those are all irreversible processes, which means that entropy change is greater than zero, so irreversible. Now, entropy, unlike energy, is not conserved because, as you can see here, it's greater than or equal to zero. Whereas if change in energy in a system is conserved, change in energy is equal to zero. However, entropy can increase, and it can't decrease. It can only increase or remain constant. All right. So let's try to mathematically define what entropy is. We can say that entropy, given that a process is isothermic and reversible, or isothermal and reversible, we can define entropy, or the change in entropy, as delta S is equal to Q over T, where Q is heat and T is temperature. And now I said this is for reversible processes, but if you have something that's irreversible, you can construct an equivalent reversible process and apply this equation, which will also give the entropy change for that irreversible process. So now, if we can apply this equation to show why, if you bring something that's hot into contact with something that's cold, that the heat direction of heat transfer will be from hot to cold. So let's just say that you have two objects here. So you have something at temperature 1, and then you have something at temperature 2. Now you want to find the direction that the heat is transferred in between these. So let's just arbitrarily define one direction as being positive. So let's just say flowing from temperature 1 to temperature 2, that's the positive direction for heat transfer. Now we can define our system as both these materials and then find the net entropy change in the system because from this heat transfer. So we have the change in entropy of the system is equal to the change in entropies of the individual materials. So for this block of material 1 here at temperature 1, we have change in entropy is equal to Q, but it's negative because it's going out of the block. So we have negative Q over T1. And then the change in entropy from T2 here is positive Q because we have Q going into this block over T2. And so this can be written as change in entropy is equal to Q times 1 over T2 minus 1 over T1. Now let's see what this means here. So let's assume that T1 is at a greater temperature than T2. That means that 1 over T1 is going to be less than 1 over T2. So if this is true, then 1 over T2 minus 1 over T1 here is going to be positive. So this is greater than 0. And then we know that by the second law, we know that change in entropy also has to be greater than 0. So these imply here from this equation, since this is greater than 0 and this is greater than 0, we know that Q also has to be positive. So Q is positive. And now what does that mean? If Q is positive, we define the positive direction of heat transfer as going from T1 into T2. So given that temperature, this temperature T2 is less than T1, we have heat transfer going from the hotter material to the colder material to satisfy the second law of thermodynamics in that entropy increases. Now, what if we say that T2 is greater than T1? So we have T2 at a higher temperature than T1. Now then we have 1 over T2 is going to be less than 1 over T1. So when we plug this back into our equation, we have, so from up here, we see that 1 over T2 minus 1 over T1 is going to be negative. So we have here entropy, change in entropy, is equal to Q times some negative quantity here. So because the 1 over T1 minus, or 1 over T2 minus 1 over T1 is negative. But no, we know that entropy here is positive. So that means that Q here must be negative as well. And that means that if Q is negative, we see that if T2 is at a greater temperature than T1, the direction of heat transfer is from T2 to T1. So in order to satisfy the second law of thermodynamics, and that entropy never decreases in a closed system, we know that it always has to flow from, heat always has to, the direction of heat always has to go from hot to cold when you have these like hot objects next to a cold object. And that follows with our conventional understanding of how like stuff in the real world works, because when you have an ice cube in water, the energy of the water gets transferred into the ice cube, which causes it to melt. It's not the other way around, where the ice cube grows bigger as it gets colder, or like, and the water gets hotter, because that would be a violation of the second law of thermodynamics. Because if you have this heat, the direction of heat opposite in the direction of what we saw here, then the change in entropy in the closed system would be negative, and that would be a violation of the second law of thermodynamics. So entropy and the second law of thermodynamics help us understand why, even though conservation of energy isn't dependent on time, it leads us to understand why certain processes are irreversible and follow like a certain direction in time. And so it favors things going from less, or so like less available, or it favors things from going from orderly or able to do work to less able to do work. And so entropy will always remain constant or increase, and it only remains constant when it's a reversible process, and it increases when it's irreversible. And this leads to the reason why certain processes function in the direction that they do, and that things don't spontaneously happen contrary to what we normally perceive.